yesterday that they, once they went through and took the notes on everything, go back and watch it a second time and just look at the notes on your paper you took and look at the clarifying things that I try to say verbally, and maybe that'll help things come together. So anyways, I'm going to run through these again. Please say, hey, if you got a reason that I could stop and make something more clear. But I want to point out kind of maybe also things that people mess up a lot at this point. Um, I've shown you a whole bunch of situations where, we want to go to the Newton's second law, um, F net equals ma thing, and then work through something like, well, how hard is the floor pushing up on the person's feet, as the answer, like for question B there. And it's super duper important that we pay attention to the wording and the phrasing. Is this an acceleration or not? And it is not. We noticed by the units, meters per second, and obviously by the constant velocity phrase. Sorry. All of the diagrams that, or all of the problems have to start with a free body diagram, because from the free body diagram, we get the left-hand side of our equation. So being a kind of a follow-up to the last unit, because it's constant velocity, we remember hopefully that the gravity force and the normal force are equal to each other. They're equal because A equals 0. And I had an aha moment with somebody when we were doing this very thing last week before the quiz. And the person was like, oh, I didn't realize, you could just take a statement of these are equal to each other and turn it into a literal equation of normal force equals force of gravity. By making these tick marks, we are literally saying you can write that equation, because equal means equal. So in this case, the force that the floor exerts, I'm going to write norm for normal so we don't confuse it with net and Fn for net or whatever. I never will represent a net force by writing Fn, because that would be confusing with normal. So if we remember that the force of gravity is mass times g, that 10 for g, it says up there that this person's mass is 50 kilograms. So the mg would be the 50 kilograms times 10 newtons for every kilogram, which means a total force of 500 newtons. We're doing that first here, not just to go back to the last unit, but because we're going to use this 500 in the next question. In this problem, this really is a result of using the net force equals ma thing with A equals 0. And if we had this is where we're going to use the free body diagram, the normal force plus force of gravity equals ma. Well, if A is 0, that means this whole side is 0. And because gravity is down, in those examples, I said, let's put a negative sign for downward direction and a positive sign in our equations for the upward direction. Well, if we just simply solve this, if this is 0 on the right-hand side, we could then rearrange this equation to say that the normal force is equal to the force of gravity, which is what we did here, kind of just straight away by saying, well, I know they're equal, and I know they got to be balanced or equal because the acceleration is 0. But this is the real justification for why we can write that as simply as we did. Any questions on that? So this is where things get a little bit different. So if I go to the next question, the acceleration happens now. There's an acceleration up, which means that the force from the floor has to be greater than the force that is pulling you down, gravity. And from this is where we say that there's a net force, and that net force is in the upwards direction. These two things are hand in hand together. If there's an unbalanced force or a net force, there will be an acceleration in that direction. The net force is not literally the normal force. the net force is the amount extra. So let's say that that gravity force was 500 newtons. Maybe the normal force is 800 newtons. If it was 800 newtons, then we're going to say the extra in that example would be 300 newtons. That's what we mean by the net force, how much more than any other force there is. So the free body diagram now for this needs to be intentional in the lengths of the arrows. So I'm going to like make this normal force one really long and the gravity one really short to indicate that the reason for the acceleration is because the normal force is so much bigger. This idea here. So we take our free body diagram, 100%. The reason we do a free body diagram is because when we go from F net equals MA to an answer, it's pulling these two forces from the left-hand side and it becomes the normal force from the top of the free body diagram. And then again, the directional negative sign because the force of gravity is down. I put a negative sign in there for the down. Then we set it up here so that we can use it here. So what do we want to find? We probably should make sure that we're paying attention to what we're looking for here. My little like laser thingy here goes away, but we're looking to find the force that the floor exerts on the person. That's the normal force. So when I write this, I can think about what it is that I'm doing and why I'm doing it. So the normal force is what I'm going to find. And I know from before, this is 500 newtons. The force of gravity on the person never changes, and that's in that downward direction. So we got to remember that negative sign. And now we got to go back to the mass. Remember the mass of the person is 50 kilograms. So mass goes back in over here, not the weight, not the force of gravity. And it's set up here that the acceleration was 4. I'll leave out the units until I get to the answer because it just kind of like gets too much going on in there. So our normal force is going to be equal to, notice that this part here is 200. And if I bring my 500 over to the other side, I have to add it. So plus 500 cancels it out on this side. I have to do the plus 500 on that side. So my answer is 700. So the force from the floor is 700 newtons. So if you remember, what I was saying up here is the amount extra is what we're calling our net force. So that's this 200 part. That's the net force in this case. But the total force from the floor is that extra that gets you accelerating on top of your everyday body weight. So your everyday body weight was 500 and the floor makes you accelerate. So it has to push harder than 500. That's the extra 200 that causes the acceleration. So the total force from the floor is 700 newtons. That supports your weight plus does a little extra to get you accelerating. Are there any questions on that?